Hello. Before we get to part 2 of the presentation on perspective, I want to talk about using projection transformations also for shadows. The mathematical techniques are very similar to the ones we use for projection for perspective, and it gives us another application of how 4x4 matrices can be used to represent nonlinear maps in certain setups. So this is best illustrated with an example of how the techniques work. So we're going to suppose the following setup. We have a point light source. It's casting shadows. So the point light source is at the point -5, 0, 0, 0. So distance 5 down the negative x-axis. Let me draw a picture here. Here's the x-axis. Here's the y-axis. The z-axis is coming out of the board. And we've got a point light source. Right here is a light source shining out light in all directions at -5, 0, 0, 5 units down the negative x-axis. And we have a wall here at x equals 1. So this is the plane parallel to the yz plane containing the points x, y, z, where x equals 1. And the light is casting shadows onto that. So if I've got a point here, which I'll call it coordinates x, y, z, the light is casting a shadow of that point onto the wall here at, I'll call it x prime, y prime, z prime. And our goal is to find x prime, y prime, z prime in terms of x, y, z. So the goal is find x prime, y prime, z prime in terms of x, y, z, and then express the map that sends x, y, z to x prime, y prime, z prime with a 4x4 matrix that acts on homogeneous coordinates. So for this, we need to get a formula for x prime, y prime, z prime in terms of x, y, z. So switch colors slightly here. We're going to use the methods of similar triangles. First of all, though, let's notice that clearly x prime equals 1 because we're on the wall where x equals 1. So let's use the method of similar triangles to find out what y prime is. So we're going to have two right triangles here. There's one here, this height is y, and there's another bigger triangle with height y prime. Both triangles are here, share this point -5, 0, 0 where the light is. The bigger triangle goes this way, the smaller triangle goes this way. This length here is 6 because we're going from x equals -5 up to x equals 1. And this length here, well, we know that this is x, so it's x minus -5 is the distance from -5 to x, which is the same as x plus 5. So by similar triangles then, we'll take y over x plus 5 is equal to y prime over 6. So that tells us that y prime equals 6y over x plus 5. And then similarly, z prime equals 6z over x plus 5. So the way to think about how this works for y and z is that first, as drawn on the blackboard, we're projecting everything onto the xy plane and looking at the similar triangles in the xy plane. To get the formula for z, we would project everything down onto the xz plane and do the similar triangles on z, and we get exactly the same formula here. So this gives us the mapping in ordinary coordinates. We're going to switch to homogeneous coordinates and represent this map by a 4x4 matrix. You'll notice, by the way, before I erase this board, this is very similar to what we did in perspective, the only difference in that previous lecture was that the central point was at 0, 0, 0 was the position of the eye. But here we're thinking of light source that's sending rays out to hit points. And on the previous talk, we were thinking of everything projecting towards the center point. But geometrically, it's the same kind of thing. We're just drawing lines out from a point to see where they intersect a plane. So before I completely erase everything, let me put the map up here that we were trying to define. We have the x, y, z is the point being shadowed, and it's getting mapped to the point x prime, y prime, z prime, which is equal to 1, 6y over x plus 5, 6z over x plus 5. So we want to go to homogeneous coordinates and get a 4x4 matrix for this. So let's, rewriting this homogeneous coordinates, we have x, y, z1, which represents x, y, z, of course. We can map it to the point, well, it could be 1, 6y over x plus 5, 6z over x plus 5, 1. But this map is not linear. We've got ratios with things involving x in the denominator. We can do it or equivalently in terms, and it's equivalent in the sense of what point in R3 it represents. Let's multiply through by x plus 5. X plus 5, 6y, 6z, x plus 5. So as homogeneous coordinates, they represent a point in R3, and we obtain that point by dividing by the w component, the last component, x plus 5 in this case. If we divide through by x plus 5, we get this, right? So it's enough to get a matrix that sends x, y, z1 to x plus 5, 6y, 6z, x plus 5. So at this point, we can pretty much just write out the matrix in a way that takes a little bit of practice to do, but isn't that hard to see. So we've got, I'll do it by rows. 1, 0, 0, 5 corresponds to x plus 5. 0, 6, 0, 0 corresponds to 6y. 0, 0, 6, 0 corresponds to 6z. And 1, 0, 0, 5 corresponds to x plus 5. And here's our matrix. I'll call it M. And so if we take M, suppose we take M and we multiply it by x, y, z1. Well, the usual thing, we take the inner product of the column with the rows, and we get x plus 5, 6y, 6z, x plus 5 as desired. So this matrix here represents the transformation of x, y, z to its shadow point, x prime, y prime, z prime. So now you might worry, however, that we cheated a little bit by using 1 here, because we just showed the matrix M works when we have a 1 in the W component. What about the case where we just have a general value W? So let's work that out here. I'll leave M on the board so we can see it here, but let's think about what should happen with X, Y, Z, W. So consider x, y, z, w. In homogeneous coordinates, of course, it represents x over w, y over w, z over w in R3. So the shadow of this point on the wall x equals 1 is given using this formula here, but using x over w, y over w, z over w instead of x, y, z. So it's 1, 6 y over w, x over w plus 5, 6z over w, x over w plus 5. We just plugged into this formula x over w for x, y over w for y, and z over w for z. I.e., if we clear the denominators with the w's a little bit, that's the same as 1 6y over x plus 5w, 6y, 6z over x plus 5w. And this is represented by, well, we could use, as before, 1 6y over x plus 5w, 6z over x plus 5w, and then a 1 for the w value. But let's instead multiply through by the denominator, and it's represented by x plus 5w, 6y, 6z, x plus 5w. And the only difference between this equation and the one I had before was we have w's, or 5w's, in place of a 5. So essentially the w, which used to be a 1, is now a w, right? So, and again, we have the following. If we take that matrix M, the same one, and we multiply it by x, y, z, w, well, that turns out to be equal to x plus 5w, 6y, 6z, x plus 5w. Exactly as desired. To see this matrix product work, we just take the column inner product with each row, and we get the product there. And this is, which represents the correct point in R2, in R3. So in this way, 4x4 homogeneous matrices can represent shadows. So in particular, you could cast arbitrary shadows of complex objects by first rendering the object, say, in 3 space, and then applying a matrix of this type to compress the object into a shadow on a surface. Okay, that's it for this presentation. Thank you very much.